And then this week's written homework is longer. I hope you've started it. If not, start it tonight. It's a little bit longer this time. So, and all the stuff is super important. So don't wait till Wednesday, or don't even wait till tomorrow. Hopefully you start it over the weekend. Start soon. It's longer. Okay, so z equals f of xy. How do we qualify that type of function? What do we call that type of function? Remember? Is it a multivariable function? And that's referring to more than one input variable, right? Or independent. Like, so your independent thing is a combination of variables, x and y. And how else could we characterize this? So it's multivariable also. Remember? Someone said real valued. Real valued? And that's referring to the output. Dependent variable is just a number, right? And we also have what kind of functions? Vector valued functions that spit out vectors, right? By the end of the course, we're going to have like 8 different combinations of these. Multivariable, single variable, real valued, vector valued functions. There's like every combination, and we're going to see them all throughout the course. So we're going to keep track of that. So this is a real valued, that's z, multivariable x and y function. All right, and then we talked about we said we're going to look at the rate of change with respect to just changing x, and the rate of change when you just change y. We call these the partial derivatives. So here are some examples of partial derivatives. Say for this function, the partial derivative with respect to x when x equals 4 and y equals 7 is 5. And the partial derivative with respect to y when x is negative 3 and y is 8 is negative 0.5. So there is a whole mess of information packed into those values. And we want to make sure we understand fully what does that 5 mean and what does that negative 0.5 mean. So we're going to just take the first 5 minutes and practice again. Get a partner and explain all the details of the meaning of that number 5 and the meaning of that number negative 0.5. Everyone's talking to somebody. Go. Alex, Winston, talk. Did you already do it? Talk. Everyone's talking to somebody. Okay, Alyssa, Miss Alyssa, how did it go? So what does the number 5 mean? Can you explain all the details about the number 5?
For any small change in x near the point 4 and x, the change in y is 5. The change in z. The change in z would be 5 times that small change.
She said for any change in x near the point x equals 4, y equals 7, the change in z would be 5 times as much as that change in x that you picked. What do you think? It's good, right? So this is the idea of rate of change, right? How fast is z changing with respect to x? So it's changing 5 times as fast as x changes in that vicinity around 4, 7. As soon as you move away from 4, 7, you might have a different rate of change. So you can't say that anymore. That's why you have to qualify that it's a small change in x. Okay, how about Alyssa number 2? How about the negative 0.5? Can you?
For any small change in y at point -3, 8, the corresponding change in z will be negative 0.5 times that change in x. Oh, it's change in y.
Good, okay. So in general, so for changes in y, z is doing what? What can you say in general? Z is changing how? Decreasing? Decreasing rapidly or slowly? Yeah, I mean, relative to what, right? So relative to the x one, it's decreasing slowly, right? Decreasing slowly in the y direction. Z is decreasing slowly in the y direction, whereas at this point, x is increasing relatively, z is increasing relatively rapidly in the x direction. 5 times your change in x. Okay, so as you're doing problems that relate to graphs, so in tables, so keep these meanings in mind, all right? So this can help you if you're you're focusing on understanding to solve the problems. Then interpreting values like this can help you kind of make progress on problems related to graphs, related to tables, okay? So we said there are 4 primary representations of these multivariable real-valued functions. We said formulas, right? So like just a function definition, a formula. We said graphs. So remember our guitar string? Our guitar string, this was the formula for the guitar string. X being the distance down the string, y being time since the string was plucked. Okay, so that's the first representation. And so we worked on, in terms of partial derivatives, we worked on finding the derivatives, right? All the same rules apply when you did the Calc 1, the mastery test, right? Remember your mastery test? All the same rules apply, except you have to imagine the other variable being a constant, right? Being a constant. So when you do the partial with respect to x, y acts just like a constant. When you do the partial with respect to y, x acts just like a constant. But other than that, it's the same derivative rules that you used and learned in Calc 1. So you're going to practice that in the web work. The next representation of multivariable functions was a surface, right? A surface in R3. For every xy combination of an x and a y, you get a real value z, and so that's like a height above the xy plane. You put all those points together, you get a surface. So here's the surface for that function for the guitar string. And last time we talked about how you can predict partial derivatives by looking at the surface. So here's the point. Here's a different point than we chose last time. Here's the point, x equals 80 and y equals 0.5. So 80 millimeters from the end of the string, 0.5 milliseconds after you pluck the string. You get this. That's represented by this point on the surface. So I want you to predict partial with respect to distance down the string, x, and partial with respect to time in milliseconds, y. For that, does that show up red? Reddish point on the surface. So take a second. Moving a little bit, that helps. So take a second to predict. What could you say about the partial with respect to x? What can you say about the partial with respect to y at this highlighted point 80, 0.5? Go. X is this. This is the x-axis here, coming out at you. Oops. Sorry. There we go. So talk to me about the partial with respect to x. Partial with respect to x. Yeah, John.
Looks like it's negative.
Negative, why?
Because when x is increasing to the right, it's going down. Z's going down.
To the right,
Or like towards us.
towards us, right? So when x is increased, make a little change in x, which means come out this way towards you. And you ask, what does z do? Does z go up, down, a lot, a little, stay constant? What do you think? I'm doing my best to give a view that you can see it. But he says negatives, meaning that z does what? Z decreases for an increase in x. Agree with that? Therefore, partial derivative with respect to x is negative. Okay? What about y? None. Or, sorry, hem. Negative, which would mean what? For a change in y, if it were negative, you'd have what? Negative change in z. What do you think? Is that what it looks like? Well, that's not what I was going for. Do you see it's kind of like in the y direction? It's kind of at the high point. Do you see that? That's what I was going for. Only in the y direction, right? In the x direction, it's coming down. Now that's to the right. But in the y direction, and you hold x constant. Let me try this. What is this? Ah, not that. What happened? Where am I? Gee whiz. Okay. There we go. Stop. X equals 80. Let's try the point difference here. I don't know what's going to be the best color. Anyway, so now we're looking at the plane x equals 80, holding x constant, and now it's the kind of the yellowish point is the point in question. So my goal was to kind of for you to see that in the y direction it's kind of at the high point. Does it kind of look like that? So then what about the partial derivative with respect to y? Harrison. Yeah, so for a little change in y, what change in z do you get at the high point? Very minimal, right? 0. So here you can kind of predict maybe that the rate of change with respect to y, the partial with respect to y, is about 0. Even though in the x direction, it's coming down. So you got to see them separately. Okay, does that make sense? So that's the kind of conversation you can have about partial derivatives related to the graph, the three-dimensional surface. Okay, so that's where we left off. And so the next thing is the table of values. So let's look at how this all plays out with a table of values. So here is a function that is heat index. So our value of is heat index is a function of the temperature and the humidity, right? Heat index is like how the temperature that it feels like, right? So there's the actual temperature it is outside, the humidity. Put those two together and you get an actual like what it feels like. That's called the heat index. Okay, so we want to estimate the partial derivative of heat index with respect to temperature and relative humidity at the indicated values here. So let's start with temperature of 90 and relative humidity of 45. Okay, so first of all, what does the 93 mean, right? So that's the value in the table. What does that mean? Yeah, so when it's 45% humidity and 90 degrees out, it'll feel like it's actually 93. That's the heat index. Okay, so that's just the value of the function. Well, now what about the rate of change? So we can look at the partial of temperature. So we can call it heat index. So we say heat index here is red, right? Heat index is a function of temperature and humidity. So we'll use I, T, and H. And so we could say the partial derivatives, could estimate partial derivatives here. So looking at the partial of I with respect to T first. And this would be at 90, 45. Now we don't have the continuous function here. We only have these discrete points of the function, so we can only estimate. So we can say it's approximately equal to what? So how am I going to come up with an estimate for what the rate of change of heat index with respect to temperature only, or the partial derivative of I with respect to T? So what would I do? Any ideas? John has an idea. Edis, what about you? Any ideas?
I would just take the average of the slope under it and the slope above it.
Okay, so
So it'd be like, X increased, or I mean T increased 4 to get to 90, then increased 3 after 90, so I just take 7 divided by 2 and call it that.
okay, so he's saying, look to a little bit to the left. So this is an increase of 4 in temperature, and this is an increase in 3 in temperature. And so, and each of those was for, index, right? So the increase of 4 in index, increase of 3 in index, for what increase in temperature? 2, right? So we're looking at increases of 2 in temperature, and seeing the resulting increase in index was on the average what? 4 and then 3, so 3.5, right? So like the average, so right around there, we're seeing an increase of index of 3.5 on the average for an increase of temperature of 2. So we would approximate the rate of change to be what? We said 3.5 over 2. Agree with that? Do you see where we're getting those numbers? So it's just here, this notation, the partial derivative notation is really nice because it really embodies the calculation that you do to get it, because it's what? A change in index per change in temperature. So we have changes in temperature of 2, and then we just averaged on either side. So change of 4, change of 3, overall, so our average change for a change of 2 is 3.5. What is that? What is it? Tell me. 1.75. What are the units on that? So what are the units on the partial index with respect to temperature? Go ahead. So again, the units are just going to follow this, right? So a change in index would be degrees Fahrenheit. Change in temperature would be degrees Fahrenheit. Should we make them go away? Cancel them out? No, right? Because we know these mean different. It's the percent Fahrenheit as it feels per actual percent Fahrenheit. So leave it as that. But even so, even if they were the exact same, you still want to leave it because it's rate of change, right? So it's rate of change. We want to communicate change in that per change in that. Okay, so I want you to do, for the same temperature and humidity, do the partial of I with respect to the humidity at 90-45. Go. You do this one. Talk if you want. Work if you want. Talk if you want. What numbers are, these numbers are hard to see? What numbers are hard? These? Is that what you're talking about? So what's the change in index per change of 5? Sound like you said 4.
So it's 2 because from 91 5, it's 4 increments.
Right.
But you,
Yeah, you could say 4 per 10,
okay. Yeah, so I got 2 over 5.
2 per 5, right? So change of 2 in index per 5 change in humidity.
Yeah.
Right. Or change in 4 per 10. Yeah, either way. So we're going to have, oh, it's not happy with my zooming in. Let's see if it'll work over here. And what are the units on that? 0.4 what?
The relative humidity, so Fahrenheit over Fahrenheit.
This is a change in index would be what unit? Index is degrees Fahrenheit. And then humidity, percent, right? Right, your change in humidity would be percent. So 0.4 degrees per percent. Okay, so this gives us the rate of change. So now what would happen, suppose we're at 90 degrees and 45% relative humidity. Suppose the temperature drops 0.8 degrees. And the humidity increases 0.2. Percent. What will the resulting change in index be, and what would you suppose the new index would be? So predict DI and the new I. So both these things happen, okay? So both, the temperature goes down 0.8 degrees Fahrenheit, and the humidity goes up 0.2 degrees. So what would the change in index be, and what would the new index be? Okay, so again, answering this question means you understood what we did up here. You understood the meaning of the values we had up here. You understood the meaning of that value and the meaning of that value. This should follow right along. You're just applying it. So I'll take attendance. You guys work on that. So if these two things both happen, predict the change in index and the new index. Go. Say that the change in I is change in index equals what? Negative 0.8? Or let's do it, you know, we said dy equals mdx, so it would be 1.75 times. And that would be the change in index due to this change in temperature. And what about the change in index due to the change in humidity? The rate of change times the little change in humidity. So I got two changes. I got the change from the change in temperature and the change from the change in humidity. And how do I get the overall then change in index? Yeah, just add them together, right? Because they're, notice like in these, you know, x and y are like perpendicular, right? They don't kind of affect each other. They're separate. So you've got all the change from the temperature changing and all the change from the humidity changing. So just add them. And what do we get for that? Negative 1.32. What does that number mean? What does that number mean? Yeah.
Changes in like the total index.
The change in the index due to
Those two changes.
those two changes in temperature and humidity. Good. All right. And so therefore, we predict the new I would be. So this should just make perfect sense. The new I is going to be what? The old I? What? plus change. The new I will be the old I plus the change. So we get what? Old I is 93. Change is negative 1.32. Therefore, 91.7 is the new index. And that's degrees Fahrenheit. Feel, right? Okay, does it make sense? This should make perfect sense. So it's all about understanding what these two numbers meant. Given a change in your independent, the corresponding change in the dependent, in this case index, is that number times as much as the change that you picked. So if I give you changes, then you're off to the races. You find the corresponding changes in index. They're separate, they're independent, so you can just add them together. You get a cumulative change from both changes in temperature and humidity. And then to get the new index, you just add your previous or your previous to the change, and you get the new field. Does it make sense? Okay, so that's using a table. That's how you use tables then to analyze partial derivatives using the table representation of a multivariable function. So if you look in the table, you can find kind of lines. You can kind of draw where the index stays constant. Like, so here's a 90, right? 90 here. And then here's 90. And then 90 somewhere in there. And then somewhere there. Somewhere there. Right? So I'm trying to draw a line of 90 as the constant. Index, right? So all these ordered pairs of humidity and temperature give me 90. So let's do it for a different number. What should I do? 85. So here's 85. Something like this. 85. Something like that, right? So when I draw these lines, what am I drawing? So 82, 82, 82. Yeah, these are like level curves, right? So this is like the fourth. If I draw lines through constant values of z, or constant values in this case of index, I'm constructing the level curves or the contour plots, which is the fourth representation of a multivariable function. So let's look at an example of that. So the point is that this is like the numeric version of a level curve graph. So finding the partial derivatives or the rates of change is going to be the same approach. Just the lines give you values of constant z. So here's a new example. This is the wind speed of in a tornado, all right? And that's a function of the size of the tornado in millions of cubic feet, and the distance from the center of the tornado in hundreds of feet. So the further you are from the center, what happens to the wind speed? So as you move up on this graph, move away from the center, wind speed goes down, all right? So I'm showing you every black line is 50, and the red lines are halfway in between those, okay? If your volume goes up, so if you increase this way, what happens to wind speed? Increases, right? So you see that for those lines. So let's pick a good place here. We're going to pick 2 and 2, right? So 2 million cubic feet and a distance from the center of 200 feet. So here's this is the size is 2, and so we're going to get that point right there. So I want you to estimate the wind speed. So this is for 2, 2. So we'll say the wind speed is a function of volume and distance from the center. So W is a function of V and D. So I want you to predict and interpret these numbers. And with units. Either making progress or you're getting help. So the function value, the partial with respect to a volume, partial with respect to distance. So just think of this just like the table of values, but now the lines show you values of constant z. But you're gonna approach it the same way that we did with the table of values to make these predictions or these estimates. Okay. See what you can do. 25. And is that the numerator or the denominator? Numerator is the change in wind speed. Okay.
And then it looks like it goes from about 2 to 2.5, so the denominator would be about 0.5.
Okay.
And then that equals
50. And if we look on the other side, do we have the same thing? So what would be different in this?
It'd be a little smaller. It'd be negative and a little smaller.
Which would be smaller? Wind speed or volume? The wind speed. Oh, right. Okay, right. Smaller change in wind speed, right? Okay. So, but this is fine. So we're just estimating. So we're saying about for 0.5 change in volume, we get about a 25 change in wind speed. So units on that, 50 what?
Miles per hour, feet per second, per million cubic feet.
Right. That's 1 times 10 to the 6th. You can just say 10 to the 6th. So about 50. Okay. And what about? Let's just throw out a number out because I want to talk about one more thing. So what are some of the numbers you guys got for this one? The partial with respect to distance from the center at 2, 2. Just throw out your, what'd you get? Negative 70.
Negative 71.
Negative 70.
Yeah.
Negative 70. What else?
Negative 66.
Negative 66. Did the rest of you get something like that? So that's negative 70 what? Miles per hour per 100 feet. Negative because when you go positive distance, when your distance increases, you're going down. So yeah, it looks to me like negative 25. Oh, but this you really have to take this into account. Yeah, so that's about right. Negative 70. So down here you have negative 50 per 0.5 change, and here you have a negative 25 per 0.5 change, so the average of that would end up being about negative 70. Okay, questions on that? Okay, so now what I want to do is I want to let volume, a change in volume be 0.1, and a change in distance also be 0.1. And what do we say? The change in wind speed, so let's just write out a formula. Can you write out a formula for the change in wind speed? Would be approximately what? So not numbers, just a formula. The change in wind speed would be? Okay, yeah, but in a formula that would calculate what this is, based on both changes, right? Right, so it'd be the rate of change, say at 2, 2, times dv plus the rate of change, don't have room, just do that, times d capital D. Right, so it's going to be the combined contributions of the change in wind speed due to change in volume, and you get that by multiplying by the rate of change, and the change in distance. Also, right, m dx, right? Y dy equals m dx, but now our y is wind speed. Our rate is this partial derivative, and our x, quote unquote, is, in this case, distance from the center. Okay, so isn't that kind of like moving this way? Isn't that like moving this way on the graph? So there's an overall, so for making a change where you have an equal change in both variables, there's a rate of change in that direction, right? So we've only talked about the rate of change with respect to our two variables, but for combinations of changes, we could say if the ratio of changes is say 1 to 1, that's like moving at this 45-degree angle. Well, there's a particular rate of change for changes in this same ratio, 1 to 1. Would you agree? And wouldn't that value be the same as if you made a change of, if you actually made that change in that direction, 1 delta. If we went a unit in that direction, then the change in z would be the same as the rate of change. Would you agree? Okay, so I'm going to take this thing right here, and notice it's a product plus a product. What is that kind of like that we've done before with vectors? Isn't this a dot product? So I could make a vector of my partial derivatives, right? And I could make a vector of the changes that we picked. But now I want those changes to result in a magnitude of 1. Because if the changes result in a magnitude of 1, then this dw is the same as the rate of change. Do you buy that? Does that make sense? So along the 45-degree line, if this is, say, the angle theta is 45, in terms of theta, how do I make a vector of magnitude 1 in the direction of theta? In terms of theta, if I want it to be magnitude 1 in the direction of theta, that would be? Unit circle, distance of 1 in the direction of theta. X coordinate would be cosine theta, sine theta, right? So if I made my change cosine theta and sine theta, that would force this to have a magnitude of 1, and would force my dw to have the same value as the rate of change, because I'm changing by a length of 1. Blank stares. So what did I just do? I just showed this formula, this dot product, will give me the rate of change in any direction specified by theta. So now we've gone from what? 2 rates of change, the partials, to how many rates of change? How many rates of change now can I talk about? An infinite number in any direction, any combination, any proportion of changes in my 2 original variables gives me kind of a direction from that center point. And if I do it by cosine theta, sine theta, then I force that change in wind speed to be the same as the rate of change. So this is now we've got derivative in any direction, not just the 2 directions of x and y. So that's a little preview of what we call Directional derivative. So we start with the partial derivatives, but through the partial derivatives, taking combinations in different proportions, we have derivatives in any direction, not just in x and y. Okay, that's a preview next time.